Hi everyone. All right, today we're going to discuss reaction mechanisms. So when we write a chemical equation to represent a chemical reaction, we usually represent the overall reaction, not the series of individual steps by which the reaction occurs. So a reaction mechanism is the series of individual steps by which an overall chemical reaction occurs. Now, knowing the rate law of the reaction helps us understand the sequence of reactions in the mechanism. So as an example, let's say that our overall reaction is occurring between hydrogen and a molecule ICl, so iodine chloride. And then we're producing 2 moles of hydrochloric acid in its gaseous state and iodine gas. Now, the mechanism for this reaction is occurring in 2 steps. So in the first step, we have hydrogen reacting with iodine chloride to produce hydrochloric acid in its gaseous state plus hydroiodic acid in its gaseous state. And then hydroiodic acid is going to react with the second molecule of iodine chloride to produce a second molecule of hydrochloric acid, and then our other product, iodine. So those 2 steps that we just went over, those are called elementary steps. So they cannot be broken down into simpler steps, and the molecules actually interact directly in this manner without any other steps. All right, now we could then come up with the overall reaction by canceling any intermediates. So in this instance, HI, hydroiodic acid, is our intermediate because it appears in the product of step 1 and it appears in the reactants of step 2. So it's being produced and then subsequently being consumed. So it doesn't actually show up in our overall reaction. So here we're showing that we can cancel hydroiodic acid from step 1 and from step 2 because again, it's being made and then consumed. Now, materials that are products in an early mechanism step, but then reactants in a later step, those are called reaction intermediates. So again, this is how we end up with our overall reaction. We start with our elementary steps, and then we cancel the intermediates, and then we just add step 1 to step 2 to get our overall reaction. So for instance, up above, you can see that on the left-hand side of our arrows, we have H2, and then we have 2 ICl, and then in the products, we have 2 HCl and 1 I2. So that's our overall reaction. Now there's another term called molecularity, and this is the number of reactant particles in an elementary step. So a unimolecular step involves 1 particle. A bimolecular step involves 2 particles. However, those 2 particles could be the same or different. And then a termolecular step involves 3 particles. But these are exceedingly rare in elementary steps. So it's not very often that we see 3 reactants in a reaction. Okay. So now each step in a mechanism is like its own little reaction with its own activation energy and its own rate law. Now down below, for our two elementary steps, both of these steps have two reactants, so they're both bimolecular. So that would be its molecularity. So each step is bimolecular, meaning they each have two reactants. And then for each reaction, we can write a rate law. So for reaction 1, our rate would be K1 times the concentration of hydrogen times the concentration of ICl. And then for step 2, the rate would be K2 times the concentration of HI times the concentration of ICl. And we're just labeling the rate constants as K1 and K2 just to differentiate them. Now, the rate law for an overall reaction must be determined experimentally. So we would have to, for instance, determine the initial rate for the overall reaction, and then compare that to concentrations of the reactants, and determine the order of the reaction that way. But the rate law of an elementary step can be deduced from the equation for that step. So you'll notice down below that the rate laws here depend on the reactants. Okay. All right, so here we have some rate laws based on the molecularity of the reactions. So in our first example, we have one reactant, and that's becoming products. So we saw so many examples of this type of reaction. But now we know that this is unimolecular because there's only one reactant. And the rate law would just be first order. So we have the rate is equal to K, the rate constant, times the concentration of A. And then in our second example, we have two reactants, but they're the same. And this would be bimolecular because there are two reactants. However, we could rewrite this as 2A is becoming the products. So the rate law would then be second order. So we would have K times A squared. Now in our third example, we again have two reactants. So this is bimolecular, but the reactants are different. So the rate law would equal K times the concentration of A times the concentration of B. So here we're kind of assuming that both are first order. And then the last three examples show termolecular reactions. So in the first one we have three reactants, but they're all the same. And again, this would be really rare. And the reason this would be really rare is, remember when we were discussing collision theory? And let's say we had a bunch of A molecules or atoms or whatever these are. It's going to be very rare that three of these molecules all hit each other at the same time. So again, termolecular reactions are rare. Now, if we did write a rate law here for this reaction, it would be third order, which is not very common, and that's why we didn't go over it earlier. But this would be K times A to the third power. Now, in our second termolecular example, we have two A reactants and one B reactant. So we still overall have three reactants. So this again is termolecular. But again, it's going to be very rare that two A molecules are going to collide with a B molecule at the same time. But if we write a rate law for this reaction, we find that it's K times A squared times B. So this reaction would be second order in A and first order in B. And then in our last example, we have 3 reactants again, but they're all different from each other. So we would write the rate law as K times A times B times C. And again, this is really rare because it would be very unlikely for 3 different molecules to all collide at the same time. Okay, so now that we can kind of see how rate laws are written according to these elementary steps, let's talk about what's called a rate determining step. So in most mechanisms, one step is going to occur much slower than the other steps. And we call that the slowest step, we call the slowest step in the mechanism the rate determining step. So that rate determining step is going to have the largest activation energy. And that rate determining step is actually going to potentially determine the overall rate law for the reaction. All right. Now, we can sort of compare the rate determining step to a traffic situation. So down below, I'm sure we've all experienced this here in Tacoma, where there's construction going on and we all have to narrow down to one lane, and that one lane of traffic is our rate determining step. So in order to get to a faster part of the highway, we have to go around this barrier. And that's the same thing for reactions. In order for the rest of the reaction to occur, the chemicals have to first get over that large barrier before they can get to the other parts of the reaction. Okay. So let's look at another reaction mechanism, and we're going to consider the overall reaction at the top. And then we'll also look at the elementary steps down below. And then we'll also look at the rate laws for these different reactions. So the first elementary step tells us that NO2 reacts with another NO2 molecule to produce NO3 and NO. Now, the rate law for this elementary step is K1 times the concentration of NO2 squared, because we have 2 NO2 molecules in the reactants. Now, this step is a slow step, so this is our rate determining step. So we'll write RDS next to it. And then the second elementary step tells us that NO3 from the first elementary reaction is then going to react with carbon monoxide to produce NO2 and CO2. And then the rate law for that reaction would be K2 times the concentration of NO3 times the concentration of CO. So these are both bimolecular elementary steps, but in the first step we had 2 of the same molecule in our reactants, and in the second step we had 2 different molecules. So the second step is fast. So once the chemicals can get over that energy barrier for the first part of the reaction, then the reaction happens pretty quickly. But again, that rate determining step, or the slowest step, is going to determine the rate law for the overall reaction. So you'll notice that the rate for the overall reaction is equal to the rate for the slowest step of the reaction. They're both K times the concentration of NO2 squared. All right, and then down below we have our energy diagram for this reaction, and you'll notice that there are two barriers or two activation energies for this reaction. And that's because there's two steps. So in the first step, reactants have to get over this very large energy barrier. And then once they get over that energy barrier, they only have to go up a tiny bit in order to get over that second energy barrier. So that's why the first step is really slow and the second step is really fast. The reactants initially need a lot of energy in order to combine. But then after that, they just need a tiny bit more energy in order to continue on. All right, so we do have two transition states or two activated complexes for this reaction. So our first one is between NO2 and NO2, and then our second one will be between NO3 and CO. Okay. So now let's go over worksheet problem 6, and we're going to consider a two-step mechanism for a reaction. So in the first elementary step, NO2 is reacting with Cl2 to produce ClNO2 and Cl. And this is a slow step. So the activation energy for that step is going to be really high. That's also going to be our rate determining step. And then in the second step of the reaction, we have NO2 reacting with Cl to produce ClNO2. And that's a really fast step. And then you'll also notice that we have two different rate constants. So remember, the first step of this reaction is really slow, so the rate constant is going to be different from the rate constant for the fast reaction. So we have K1 versus K2. So now, what is the overall reaction? After we've determined the overall reaction, we're also going to, well, I guess during the process of finding the overall reaction, we're going to identify the intermediates in this mechanism. And then we want to determine the predicted rate law for this reaction. Okay, so let's determine the overall reaction. So we want to try to get rid of any intermediates. So you might notice that Cl is showing up in the product of, or in the products of the first step and in the reactants of the second step. So that tells us that Cl is being used up pretty quickly. So it's not going to hang around. So we're going to cancel Cl, and then we'll just write what's left over. So we have two NO2 molecules on the left-hand side, and then we have one Cl2 molecule on the left-hand side. And then on the right-hand side, we have two ClNO2. So again, we're just essentially adding those two together. Oh, and I forgot my state of matter. Okay, so that's our overall reaction. So 2NO2 reacts with Cl2 to produce 2ClNO2. Now, what was the intermediate? Well, we already said it was Cl. So that was our intermediate in this mechanism. So what is the predicted rate law for this reaction? Now remember, it depends on the slow step. So the slow step in this case was the first one. So our predicted rate law is K times the concentration of NO2 times the concentration of Cl2. So the rate determining step is what determines our rate law. Okay. And I'm just going to draw an arrow to really hit that home there. Now, sometimes we need to validate a mechanism. And in order to validate a mechanism, two conditions must be met. So first, the elementary steps must sum to the overall reaction. So for instance, in the last example we just did, that was true. The elementary steps did sum to the overall reaction. But additionally, the rate law predicted by the mechanism must be consistent with the experimentally observed rate law. So again, the rate law that we would predict has to match the experimentally observed rate law. Okay. Now, sometimes a reaction will start with a fast step, and then the rate determining step will be after that. So that might kind of look like that, where our largest energy barrier is second. Now this is going to cause some problems because in that instance, the rate determining step may contain intermediates. So for instance, let's say step 1 is A plus B, and that's becoming C plus D. And then let's say in step 2, we have then C plus B is becoming D. So the second step here is our slow step. So that's our rate determining step, which is fine. That does happen. But if we write the rate law for that, that's going to give us K times C times B. And C, you'll notice, is an intermediate. Now, unfortunately, we cannot have an intermediate in our rate law because, remember, an intermediate is going to be produced and then consumed. So the concentration of C would be 0, which is going to mean that our rate is 0. So we can't have an intermediate in our rate law. However, when a previous step is fast or rapid and reaches equilibrium, that means that the forward and reverse reaction rates are equal. So we could write a rate law based on the reactants in step 1. So substituting the rate law of the rate determining step, or substituting into the rate law, will produce a rate law in terms of just reactants. So what we could do is write the concentration of C in terms of A and B. So maybe it would look like, K times A times B, and then we could just plug that into C. And that way we can avoid having C in our rate law. So this probably is a little confusing because it's very abstract in a way. So we'll go over some examples as well. All right, so our first example, we have 3 steps in this reaction. So in the first step, 2NO is 2 NO molecules are combining to form N2O2, and that's a fast step. So that's not our rate determining step. And then in step 2, hydrogen is reacting with N2O2 from the first step to produce H2O and N2O. And this is our slow step. So that is our rate determining step. So again, our slow step is occurring after a fast step, which is going to cause some complications, which we'll talk about in a second. And then in our last step, we have hydrogen again reacting with N2O to produce H2O and nitrogen. So that is our another fast step. All right, now remember from a few slides ago, in order to validate a rate law, there are two conditions that must be met. So the first condition is the three steps here have to add up to an overall reaction. Okay, so let's write our overall reaction. Now let's try to first identify any intermediates. All right, so N2O2 appears in the products of the first reaction and the reactants of the second reaction. So that's one of our intermediates. And then N2O appears in the products of the second reaction and in the reactants of the third reaction. So that's our other intermediate. So we can cancel all of those. And then we're just going to add together everything that's left over. So on the left-hand side of all of these different arrows, we have two NO molecules. And then we also have two H2 molecules. And then on the right-hand side of all of our arrows, we have two H2O molecules and one N2 molecule. Okay, so that's our overall reaction. So the first condition here then is met because that is in fact the overall reaction that occurs. So normally you would be given that overall reaction and you would just have to verify that these elementary steps all add up to the overall reaction. Okay, so the first condition is met. Now, the second condition, so let's go back to our conditions here. The rate law that's predicted by the mechanism must be consistent with the experimentally observed rate law. Okay, now remember that typically we want to use the rate determining step to write our rate law. However, in this case, our rate law, which is K2 times H2 times N2O2, it contains an intermediate. And that is not going to match our observed rate law. In fact, our observed rate law so this is determined experimentally. This is equal to K times H2 times NO squared. So these two do not match, and we need to make sure that they actually match each other. Okay. So again, our first condition was met. This is our overall reaction, and it's the same as what we determined on the last slide. But again, our observed rate law that was determined experimentally does not match what we would predict from our rate determining step. Now, we can use the fact that the first step is at equilibrium, and we can rewrite our rate law in terms of the reactants of that first step. So we're going to utilize this first step and its equilibrium state to, excuse me, to rewrite N2O2 in terms of NO. Oh, and I think there's something missing there. So there's a forward and a reverse reaction in that first step because it's at equilibrium. So the forward direction has a rate constant of K1. The reverse reaction has a rate constant of K minus 1. So what we're going to do is set the rate of the forward reaction equal to the rate of the reverse reaction. And this is for step 1. So the rate of the forward reaction is equal to K1 times the concentration of NO squared, because we have 2 NO molecules in the reactants. But because this equation is at equilibrium, we can also consider the reverse reaction. So the rate of the reverse reaction is equal to K minus 1 times the concentration of N2O2. Now, again, because this reaction is at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. Because remember, in order to reach equilibrium, the rates have to equal each other. So let's set K1 times the concentration of NO squared equal to K minus 1 times the concentration of N2O2. Now remember, our ultimate goal here is to replace N2O2 in our rate determining step, rate law. So we're going to do that by seeing what N2O2 is equal to here. So we're just going to rearrange this equation. So the concentration of N2O2 is equal to K1 over K minus 1 times the concentration of NO squared. All right. So let's plug that in to our original rate law. Okay, so we're going to plug that in. So, we said that the concentration of N2O2 is equal to K1 over K minus 1 times the concentration of NO squared. All right, so now our rate, which was originally equal to K2 times H2 times N2O2, will equal K2 times H2 times K1 over K minus 1 times NO squared. Now, what we're going to do here is just set K equal to K2 times K1 over K minus 1. So we're really just going to combine all of these different rate constants into one rate constant. And that's totally valid to do. It's just magic. We're just going to combine them all together and call it a day. All right. So we end up with some rate constant times H2 times NO squared. And that is equal to our observed rate law. All right, so the second condition has been met. We have validated our reaction mechanism. And the reason that we might need to validate a mechanism really is just sometimes it's guesswork. Sometimes we don't really know what's going on, and so we just have to make some guesses or some estimations. And then in order to validate those estimations, we'll go through this process where we first make sure that the elementary steps add up to the overall reaction. And then we also want to make sure that the observed rate law matches our predicted rate law. All right, so let's go through another example just to make sure that we've got this down. I actually still remember learning this in college and being very confused, and it took a lot of practice for me to really understand it. So if you're feeling a little confused, don't worry. It's normal. All right, so ozone naturally decomposes to oxygen according to the following reaction. And the experimentally observed rate law for this reaction is K times the concentration of ozone squared times the concentration of oxygen to the -1, which we have not seen yet, but that is possible. So to show that this proposed mechanism is consistent with the show that this proposed mechanism is consistent with the experimentally observed rate law. I'm a little tongue-tied today. All right, so we have two steps that are proposed for this mechanism. In the first step, it's proposed that ozone is decomposing into O2 and then a single oxygen atom. And you'll notice that this step is at equilibrium, so there's a forward reaction and a reverse reaction, and there are also two rate constants. So K1 is for the forward reaction, and K minus 1 is for the reverse reaction. And this is a fast step. And then in our second step, it's proposed that ozone then reacts with a single oxygen atom to produce 2 molecules of O2. And this does not have an equilibrium here. It's just a forward reaction with a rate constant of K2. Now, the second step is our slow step. So it's our rate determining step. Now remember, we need to meet two conditions to validate this mechanism. We need to add the two elementary steps together and make sure that they add up to the overall step. Or the overall reaction. And then second, we need to make sure that the predicted rate law equals the observed rate law, so the experimental rate law. Okay, so let's add the two elementary steps together and make sure that they add up to our overall reaction. And I'm just going to leave out the states of matter because that's not what we're really concerned with here. Oh, I missed a reactant. Okay, so let's add these two together. So do you see any intermediates? And what is the intermediate? So hopefully you said the single oxygen atom. So we're going to cancel that because it appears in both the products and the reactants. So now we'll just add together what's left. So we have 2 ozone molecules on the left-hand side and 3 O2 molecules on the right-hand side. And this matches our original overall equation. All right, so the first condition has been met. Perfect. So now the second condition, we need to make sure that the predicted rate law equals the observed rate law. So the predicted rate law depends on the slow step. So according to the slow step, our rate should be K2 times the concentration of O3 times the concentration of O. But this does not match our observed rate law, which is up above. Our observed rate law that we determined experimentally is K times the concentration of ozone squared times the concentration of oxygen to the -1. All right. However, to prove that these two are equal, what we can do is figure out, okay, what is the concentration of oxygen equal to? And we're going to use our equilibrium elementary step to do that. Okay, so in our first elementary step, remember that the rate of the forward reaction will be equal to the rate of the reverse reaction. And we can only say this for an equilibrium equation. So for instance, in the second step here, there is no reverse reaction. So we could not do the same thing there. All right, so the rate of the forward reaction is equal to K1 times the concentration of O3. And then the rate of the reverse reaction is equal to K minus 1 times the concentration of O2 times the concentration of O. And again, if we were considering the reverse reaction, we're considering O2 and O as the reactants. So that's why those would appear in our rate law. Okay, so let's set these two equal to each other. And now remember, we want to solve for the concentration of O, oxygen, because then we can substitute that into our predicted rate law. So we're just going to rearrange and solve for the concentration of O. So that would be K1 times the concentration of O3 over K minus 1 times the concentration of O2. Great. So now let's plug that into our predicted rate law. Oh, I jumped ahead. And I'm just going to divide this here. So we've got K2 times the concentration of O3, and then we're plugging in what we found before. So K1 times the concentration of O3 all over K minus 1 times the concentration of O2. All right, now again, we can just combine all of those K values into one big rate constant. So we'll just put a K there. And then we have two O3s here, so we'll just square the concentration of O3. And then in the denominator, we have O2. So if we rewrite this, we can say that the rate is equal to K times the concentration of O3 squared times the concentration of O2 to the -1, because it's in the denominator. And now this matches our observed rate law up above. So the second condition has been met. So that validates our mechanism for this reaction. So there's a lot of work that can go into these rate laws, especially if there's multiple steps to your equation or to your reaction. So hopefully this made a little bit of sense. Again, if you have any questions, you can always email me or set up an office hour with me. But otherwise, our last part of chapter 14 involves catalysts. So that will be a pretty short lecture video, and I will see you then.